Frank-Wolfe and Structural Friends.
Thank you very much. So I'm delighted to be here, especially because I was making my way here for 47 hours. So being here is quite nice, actually. And I want to thank the organizers, Martin, Zaid, and Federico in particular, for putting together this workshop. It's just an excellent avenue. So I have a bunch of slides, and for those of you who might be getting bored or something, I wouldn't worry about it because I think I'll be able to confine my remarks to 30 minutes maximum. I also think in the spirit of what I understand NIPS conferences to be, so please interrupt or ask questions or suggest things during this talk. So let me begin. Oh, and I also want to say thanks to Paul Grigas, who's a PhD student at MIT, Rahul Mazumdar, who's in the statistics department at Columbia. I've been collaborating with them on a lot of the material that's in this talk. Okay? But this talk represents some of my own work with Paul and Rahul, but also the work of others. And I don't intend it to be comprehensive because I am not a comprehensive scholar of the literature, as some of you might object to. But I want to highlight a few things that I think are particularly interesting about what's been happening in this arena. Okay. So here are some of the topics. One is I want to do a quick review of the Frank-Wolfe method. I want to talk about a modern application. People have known about this for several years, low-rank matrix completion. Then I'm going to talk about Frank-Wolfe and its connections to a particular method of Nesterov called the dual averages method, and also greedy coordinate descent and dual averages. So this is the greedy coordinate descent I consider a structural friend of Frank-Wolfe. Okay? And then if I have time, I want to talk about Frank-Wolfe for stochastically smoothed optimization. This is work by George Lan at the University of Florida that I consider to be quite interesting. Okay. So maybe I'm not going to repeat what Zaid said, but I had my own slide of why there's so much renewed interest in the Frank-Wolfe method. I just want to talk about these points down here. The setting usually in which it's particularly attractive is when we need only moderately high accuracy solutions. And for a lot of the applications that Zaid mentioned, as well as these here, that is definitely the case. Also, these methods, the settings typically are huge scale, tens of thousands or 100,000 or a million variables, whatever. And so elementary operations themselves become quite expensive. All right, but Frank-Wolfe is good for this. And then also the structural implications, sparsity and low rank, which Zaid had alluded to as well. Okay, so here's the method in my version of the notation. Okay, so the problem of interest is a convex problem. F star minimize f of x subject to x is in some ground set P. P is convex and compact. F is convex on P. Let x star be any optimal solution. And we assume f is differentiable on P. And we assume it is easy to do linear optimization on P for any objective function C. So I can easily solve this problem. Argument some linear objective on the set P, and the solution will be x tilde. Okay? So and then there's the problem again, and then here's the method. And what is in red is unnecessary, but it's really just sort of what I would call accounting. Okay? And for those of you who are just coming in, I'm just kind of reviewing the basic Frank-Wolfe method. And also for those of you coming in, I would say, I laid the ground rules earlier. Please interrupt with questions or comments or objections, but save your objections till later maybe. Okay, so here's the basic method. We initialize it at some point x0, we set the counter to 0, and we have some lower bound on the optimal value. Maybe that lower bound is minus infinity. So I just need to set it to something. So I could set it vacuously, essentially. Okay. We compute the gradient. Then we solve the following linear optimization problem and compute x tilde k. And then we can, if we want, update a lower bound that's given by the convex, just through the convex structure of the problem. It's the minimum of the minimum. This should be maximum. The maximum of the previous lower bound and what you obtain at the point that solves the linear optimization problem. And then you set your new point essentially to be a convex combination of your current point and the solution to the linear optimization problem. So if I set alpha bar between 0 and 1, and I move from my current point, and if I set alpha bar to be 1, I go all the way to the solution to the linear problem. Okay? And that's Frank-Wolfe. Okay? There's a lot of different ways you can set step sizes. I'm just going to briefly mention the most often used ones. There's sort of what I would call the recent standard, which is set the step size to be 2 over k plus 2. I should point out this is quite recent in one sense, although I had an email exchange back in 2007 with Arkady Nemirovsky, wherein he told me and then showed me a proof with this step size. So, but of course, he knows everything anyway. Okay. And he also told me he never really, because I asked him about this a year ago. He said he never shared this with anyone, and he had never written it up. So exact line search is to solve this one-dimensional optimization problem exactly. Simple averaging would be to, this essentially says that the next, basically says your next point is the simple average of all your previous points. Okay? Constant step size. So this arises in comparing this to certain problems in certain methods for solving linear regression. And then a quadratic approximation step size, what I call QA, that essentially solves the quadratic optimization approximation to the problem over the line segment. And then the one actually I'm the keenest on at the moment, although that's a little bit self-serving, I admit, is a dynamic strategy, sort of that, and I won't go into the details on it, but it's determined by some history of the optimality bounds. Okay? And Paul Grigas is going to be talking about that later today. Okay. Here's a simple computational guarantee, one of many different flavors of computational guarantees for the Frank-Wolfe method. If the step sizes, say, are chosen with the recent standard, then for all k it holds that your optimality gap is at most 2c over k plus 4, where c is, say, the Lipschitz constant, which I'll get to shortly, times the diameter of the set squared. Okay? There's similar guarantees hold when step sizes are determined by line search, quadratic approximation, or the dynamic strategy. Okay? So what is the Lipschitz constant? What is the diameter? So let us have a prescribed norm on the space. The dual norm is just the dual norm. Let bx rho be the ball centered at x with radius rho. Then the diameter is going to be the maximum distance between 2 points in the set. Okay? And L is the Lipschitz constant for the gradient on P. So there's some constant L for which differences in the gradient are at most L times differences in the points. Okay? Now there's a curious thing here that's, quote, going on or not going on, which is sort of, as I've written it, this bound depends on your choice of norm, but the algorithm does not depend on any choice of norm. Okay? And so, in fact, one can do the following. You can actually give norm invariant versions, actually, of all the results probably in this room. Okay? And so one way to do this is to, I think of this as Clarksons curvature constant. You can let CL be the smallest non-negative scalar for which this inequality holds. Then that is going to be at most L times the diameter of P squared for any norm. But this constant CL doesn't depend on any norm, and you can just plug that right in here. Okay, let's just give you an example. Okay, see how am I doing on time? Okay. My favorite topic on the planet is actually symmetry issues in convex sets, all right? And let me just, since I guess I can use this, is that right? Okay, so if I have a convex set, say looking like this, okay, that's at an intuitive level, this point here is pretty symmetric in the set, whereas this point here is not, okay? This can be made precise by basically sort of saying, so this would have a symmetry value of almost 1. This would have a symmetry value of almost 0. And the way you measure the symmetry value is you look at all chords in the set, say passing through your given point, okay? And you look at the ratio of the smallest to the largest. And you look at the smallest of all of those, and that's the symmetry of a point in the set. And that's embodied in this definition, okay? But the much better version of it is the picture, all right? And it's a number between 0 and 1, okay? And in fact, if x is in the set, the symmetry of the point in the set is always bigger than or equal to, if I have a norm, say the distance of the point to the boundary, which say is here, divided by the diameter of the set. So the bottom statement here, this is a norm-free object, this is a norm-related object, okay? All right. You can also talk about strongly convex functions, and said that's going to come up actually in a few more slides, much more importantly. So I'd ask you to try and absorb this notation. So we'll say a function is U strongly convex on P if there exists a positive constant for which, and so f for all x and y in P, f of y, well, this first part here we know from convexity, that f lies above the tangent plane. But now it's saying it lies above the tangent plane plus this, and you can think of this as a sort of a quadratic piece, even though the norm is not necessarily a Euclidean norm. Okay, but you sort of think this is growing quadratically in some norm. All right, so that's mu strongly convex. And so here's a result that's essentially, I would say, due to Wolfe of Frank-Wolfe. Okay, but so he wrote this paper in 1970, actually, but he made some mistakes. Okay, and those mistakes got corrected by Guélin and Marcotte in 1986. And so here's the result. It says, suppose step sizes are chosen using either the quadratic approximation rule or the line search, not the recent standard. Okay, then for all k it holds that, and let me just decipher this for you. Okay, so this says this object on the left is what we've already seen. So 2 times the Lipschitz constant times the diameter squared divided by k. That's the sublinear convergence. But here's linear convergence over here. But before you get too excited about linear convergence, all right, let's just see what's going on here. So first of all, u here has to be positive. Otherwise, this term is just 1, and I've said nothing. All right? This just says subsequent iterates do better than the current iterate. Okay? Big deal. Okay? So u has to be positive. So the function that we're working on has to be strongly convex. And also rho, which is the distance of the point to the boundary, has to be positive. So this really only pertains to the case where the optimum is in the interior of the domain of under question. Okay? So if your function is strongly convex, and if your solution is in the interior, you get linear convergence. All right? And that is that. Okay? Now, this is a normed representation of the problem, but I can replace what's going on here with the symmetry of the point, in the symmetry of the optimal solution in the set. So I can actually replace it. This is 1 times, I need a different curvature constant. I need the ratio of 2 different curvature constants, the symmetry squared. And so this is sort of a norm-free representation of all of this. Okay? So here's, any questions or no? Oh, yes?
Does it make any sense to do Frank-Wolfe for the optimal solution in the interior? You can simply do gradient descent and find it.
Yeah, I mean, in other words, right, so the interior is a particular, right? Usually we don't know beforehand the point is in the interior, but if the point is in the interior, okay, there's other, so I mean, on the downside, sort of think if the point is in the interior, why consider it a constrained problem? Okay. On the other hand, if the point is in the interior, we could still take this sort of one interpretation of this result, okay, is that if Frank-Wolfe is the only method at your disposal, for instance, you can easily do linear optimization on the domain, but you can't necessarily do projection or who knows what else you might want to do. Okay.
If you are in the interior, you don't need to do any projection.
Yeah, I mean, yes, I mean, you could do, I mean, right, another way to look at this, frankly, especially given your remarks, sort of is that, you know, this is mimicking what's going on in, you know, in the linear convergence theory of steepest descent. Okay, so let me just quickly go over with you what I would call a prototypical example. So, right, there's tons of different applications. I don't know about tons, but there's at least many different applications of Frank-Wolfe. But here's one of the more modern ones. So, folks, there's seats all over the place here. So please come on in. Okay. So let me just review what probably many of you in this room know, but presumably some of you in this room don't know, which is low-rank matrix completion. So, and again, this is just an example of the good use of the Frank-Wolfe method. So let Z be a partially known data matrix. Let omega denote the entries of Z that are known. You could think of, I think of this as I have a giant matrix of Netflix users and movies, and I know people's preferences for the movies they've seen, okay? But I don't know their preferences for the movies that they've not seen or not bought via Netflix, okay? Let Z omega denote the entries of Z indexed in the known category. And then here's the problem. I can't really get into why it's set up this way, but I want to solve for Z star, which essentially is, let's find a matrix that's close to this matrix Z. Z is the data matrix, whose rank is small. All right, so that's matrix completion. So, and I say we aspire to solve it, okay? And here it is. So the typical thing is to replace the rank constraint by a constraint or a penalty on the nuclear norm of a matrix X. So what is the nuclear norm of a matrix X? Well, you can think of X as being decomposed with its singular value decomposition into U dV transpose, where U and V are orthonormal matrices, and D is a diagonal matrix composed of the non-zero singular values of X. All right? So in other words, so this is an efficient representation in the sense that essentially the matrix D only has rank R if X has rank R. Okay? And then the nuclear norm is just the sum of the singular values. Okay? Again, X is U dV transpose, D are the non-zero singular values, the nuclear norm is the sum of the singular values, and let's let B0 delta be, say, the delta ball around the origin in the nuclear norm. Okay? So we aspire to solve this problem, but this problem is a very hard problem. It's like NP hard or NP complete, or what I would call NP difficult. Okay? Instead, let's solve the following nuclear norm convex optimization problem indexed by delta. Let's minimize this quadratic function, which is how close the matrix X is to Z among all the known values, subject to the nuclear norm is at most delta. Okay? Now, this problem aligns very well for the Frank-Wolfe algorithm. Okay? Here it is again. So, for instance, for the objective function computation, okay, if I look at the gradient is just the projection onto the omega indices of X minus Z. Okay? And so it's just X minus Z, those indices. Okay? So it's I would say it's, quote, viable to compute in the sense that, especially if omega is relatively small, okay, then we don't have to do much computation to obtain it. Even though X, for example, you know, maybe millions or 10 million entries, right, because it's a matrix. So if it's, you know, 100,000 by 100,000, it's 10 million. Okay. It doesn't have to be square, by the way. Okay. Furthermore, linear optimization subproblem here is viable. So you give me any matrix C, I'll define C dot X to be the trace of C transpose X. This is just basically the inner product of two matrices. All right? And then if I want to solve the optimization problem, minimize a linear function of X over the nuclear norm ball, that's very, I would say, quote, very easy, okay, in the following sense. So I compute the largest singular value of C associated with the, and I also compute the left and right normalized eigenvectors U1 and V1, all right? And then X tilde is just minus delta U1, V1 transpose, all right? And so, you know, say compute the largest singular value with associated left and right normalized things. So how hard is that? Well, it's hard, it's easy, but it's also not so easy. So, but there's usually obtaining sort of the very high eigenvalues or singular values and the very low singular values are easy to do by Lanczos methods and other stuff like that. This is not my area of expertise, but this is usually viewed as a very simple operation. Okay. All right. So instead of working directly with the nuclear norm ball, we actually could lift this problem if we wanted to into the space of spectrahedra. And so let me just outline that quickly. So it turns out the statement, the nuclear norm of X is at most delta, is the same as there exist two matrices W and Y for which this matrix A, WX, X transpose Y, is positive semi-definite and its trace is at most 2 delta. So this is like an exercise. You can find this in Bental and Nemirovsky. You can find this probably in Boyd's textbook. You can find this probably in the handbook on semi-definite programming, stuff like that. Okay? So we could solve the equivalent problem on the spectrahedra. Well, now in addition to X, I have matrices W and Y, and I want to minimize my quadratic. And so this is the intersection of the semi-definite cone here just with a trace constraint that basically makes things nice and bounded. Okay? And so here is an equivalent way to sort of solve that nuclear norm constraint problem over the nuclear ball. Okay? However, the matrix dimensions here are doubled. Okay? So that's not fun. Okay? I mean, it turns out many necessary Frank-Wolfe operations can be done in the original dimensions, though, in this version of the problem. And then there's something that Wolfe introduced that was then analyzed by Guélin and Marcotte called away steps, that they're much more forward to work with up here, essentially, than in the otherwise more efficient representation of the problem down in the space of the nuclear norm ball. Okay, all right. So now I want to talk about two more topics. But the next topic is actually, there's sort of two different things, and then I'm going to unify them, I hope. All right. So this really has to do with Nesterov dual averages method. Okay. And I'm going to show here, this is really work of Paul Grigas, and with a little help from Rahul Mazumdar and myself, on connecting Frank-Wolfe to dual averages, connecting greedy coordinate descent, which is an algorithm I haven't mentioned to you yet, okay, to dual averages, and a unified treatment that yields some interesting things. Okay? So let's just take a break from Frank-Wolfe for a moment, okay, and talk about the following maximization problem. So H star is going to be the maximization of some concave function over some convex domain Q. All right? So I've just want to solve that. Now I'm going to, and H is presumably non-smooth. So I'm going to attack it with a non-smooth method. Just want to check out the time here. Doing all right. Am I? Yeah. Okay. So dual averages algorithm for this problem. So the dual averages method is a method that a lot of people do not study. Okay? And why is that? So it is more powerful than proximal methods like mirror descent. Okay? But it is less intuitive. So all I want to try and do here is give you a tiny bit of intuition onto why it might be so good. But essentially, it is as good or better than anything related to like mirror descent or other prox methods for non-smooth problems. Okay? All right. So we initialize at some point. I'm going to just choose some other object, x bar. You could think of setting this to 0 if you really want. And I'm going to set some object to 1. Okay? At each iteration, I have my current point lambda k, and I compute a subgradient. Okay? I choose a step size, and I increase. This is going to be a weighted combination of step sizes. Sorry, not a step size. Yeah, I choose a step size. This is going to be a weighted combination of gradients. Hence the notion dual averages. Okay, I'm taking sort of an average or a combination of gradients, and I'm going to call that thing x bar k plus 1. And then I'm going to choose, I'm going to increase this counter, or I might keep it the same. And my new point, I'm going to solve, maximize this. And so this is going to be sort of my combination of gradients that I've accumulated. Okay? And then down here is going to be d of lambda, where d is just a prox function. That's a sigma strongly convex function on Q. Think of it as 1/2 lambda transpose lambda if you want to be Euclidean. Okay? And sort of this is kind of like a steepest descent kind of step. Okay? And that's the method. Okay? Right? It looks like it's sort of starting from scratch all the time because the update doesn't explicitly depend on the previous, on the current iterate, but it depends on the history of gradients. Okay? And Nesterov wrote this beautiful paper where he, A, invented this method, and B, analyzed it, and C, showed that it could be applied to everything. Well, almost everything. We're doing the everything part. Okay. So now let's suppose H has min-max structure, meaning H is, say, the minimum of some x and p lambda transpose AX. Okay. And then if I have min-max structure, I solve my x tilde k to be the arg min here. Okay. Then the gradient is actually ax tilde k. You can prove this directly. It also is a corollary of a much more difficult result to prove called Danskin's theorem. But you don't need Danskin's theorem to estimate this. So now the dual averages method, and then I write in here that computing this subgradient is done by, well, I take arg min x and p of x tilde k, and gk is then ax tilde k. Okay, so this is just saying how I get my gradient if H has min-max structure. Now I want to tease you a little bit here. If you look at this step here, this looks like Frank-Wolfe, doesn't it? Okay, x tilde k is arg min of some linear function of x over the set P. All right, so it gets deeper than that. And so this is the rest of the algorithm. And then while I'm at it, I'm going to throw in some accounting. So while I'm at it, let me keep track of these x tilde j's. Okay, let xk be the weighted sum of these x tilde j's, where the weights now sum to 1. All right? So now let's return to Frank-Wolfe. Okay, here was the Frank-Wolfe problem. F was L smooth. And because F has an L smooth gradient, I can always write F in conjugate form. That is, there's some matrix A, some ground set Q in another space, and some, I'll call it prox function, for which f of x is this conjugate form. Okay? And what I'm not necessarily, we may know A, Q, and D for a lot of problems of interest, or we may not know them. And we may never need to know them. I just want you to know they are there, whether you know it or not. Okay? In fact, if f is globally smooth, D is going to be a sigma strongly convex function, where sigma is the norm of A squared over L. That's a result of Nesterov. Okay. All right. And computing the gradient of f is done this way. It's just going to be my A transpose lambda k. I won't bore you with this. But now, here's the Frank-Wolfe algorithm with the gradient computation in conjugate form. Again, you may not know the conjugate form. You may just know it's step 1. I just give me the gradient. Okay, but at least existentially, there is some Q, A, and D, and there's some lambda k's for which I solve this problem, and the gradient is A transpose this. Okay? And that's Frank-Wolfe. And now here's the theorem. Frank-Wolfe is an instance of dual averages. So this is really due to Paul Grigas at MIT, although there are results that are of a similar flavor, but also different due to Francis Bach. I've never met Francis Bach. I don't know if you're in the... Ah, very nice to meet you. Okay, all right. So let xk, x tilde k, lambda k be the iterate sequence of Frank-Wolfe in min-max form with appropriate initialization. Then the Frank-Wolfe iterates correspond exactly to dual averages iterates for solving the following shadow problem. This is not a dual problem. This is a shadow problem. This is just a different problem that you don't know it, but it's there. Okay? And that problem is maximize the minimum of lambda TAX over lambda in Q. Okay? But I need to tell you what the dual averages alpha and beta sequences are, and they're given by these formulas up here. Okay? So to me, the moral of this story so far is, okay, whether we know it, whether we care or not, whether we explicitly know the structure, there exists structure for which Frank-Wolfe is a special instance of Nesterov dual averages. Okay? The equivalence holds even if F is not globally smooth, and we don't necessarily need to know or compute with the conjugate representation of F. Okay? Okay. But there's more. Okay? Now let's focus on a different algorithm, the greedy coordinate descent method for unconstrained smooth optimization. Okay? So we're going to leave the world of Frank-Wolfe now entirely for the rest of this talk, actually. Okay? Consider the following unconstrained convex optimization problem. Minimize f of x, where x is in Rn. Okay? We're going to assume f has L-smooth gradient. We can always write it in conjugate form, or not. I mean, we can if we know it, okay? But the form exists, okay? And we can compute gradients that way if we know it. So here's greedy coordinate descent. The greedy coordinate descent method just says, compute your gradient, look at the component of the gradient that's largest in absolute value, take a step in that coordinate, okay? And so now let me make it look slightly more complicated, okay? You start at some x naught, you compute the gradient, which if your problem is in conjugate form, are these computations, okay? To figure out which coordinate you're going to go in which direction, you, in a sense, trivially solve the following problem. Let x tilde k be the minimum over the L1 ball of the gradient inner product with x. Okay, so this gets you the largest coordinate and the right direction, and xk is just updated by a simple step size. All right? So that's greedy coordinate descent, a very popular recent method whose analysis, I should say, is a bit elusive right now. So we have some good results on greedy coordinate descent from a computational complexity or computational guarantee perspective, but I'd say we don't have enough. So to me, this is a very active area of work. Okay? And here's the theorem. Greedy coordinate descent is an instance of dual averages. Okay? So let xk, x tilde k, lambda k be all these objects computed in here. Okay? Using step sizes alpha k, and define my beta k's always to be 1. So it's just a string of 1s. Then greedy coordinate descent iterates correspond exactly to dual averages iterates for the following shadow problem. Again, this is not a dual problem. Okay? And in fact, what's interesting is in certain instances, this problem is trivial. We would never set this problem up to solve. Okay? But there's good implications. So H star is maximize minus the infinity norm of A transpose lambda over lambda in Q. Okay? All right, so let's just turn this around and make it look interesting. H star is really, it's just the minimum of the infinity norm of A transpose lambda. Okay? And furthermore, and sort of this is the really interesting thing, okay? The objective function values, okay, that greedy coordinate descent is trying to work on at each iterate exactly corresponds to the infinity norm of the gradient of my original problem of interest. So in other words, and again, this is, we don't need to know A, we don't need to know Q, we don't need to know D to state this result. This result says there is a problem out there for which greedy coordinate descent is directly attacking, trying to find a zero, trying to minimize the norm of the gradient of my original problem. which is just what we want to do, right? I either want to minimize f or I want to minimize its the norm of its gradient. Okay? Okay. So again, I'll say here, not by design, but through the dual averages structure, okay? Not by design. This is sort of an accident. I mean, nothing is an accident, but at least it is not by intent. Greedy coordinate descent is driving the gradient of my function of interest to 0. Indeed, using, say, the complexity theory for dual averages, which I have not reviewed for you, okay, you get sort of here is one of many kinds of results we could get. Let x star solve our original unconstrained problem. Lambda star solve this, and then define step sizes this way. Then, in fact, greedy coordinate descent, okay, after k iterations, the norm of the gradient, which we want to drive to 0 because we're trying to minimize f, okay, is at most this, and here is the k plus 1. Okay, so here is k. So after k iterations, right, this thing is going down as square root of k. All right. This structurally can't be beaten, but actually, I'm not sure of that. I would say at the moment, I take that back. But this is structurally sort of a typical non-smooth optimization analysis. Okay. So dual averages has as instances both what I would call constrained greedy gradient, Frank-Wolfe, say in an L1 norm setting where we're minimizing the gradient over the set, and unconstrained greedy gradient, greedy coordinate descent. Okay. And there was nothing special about the one norm and the infinity norm, of course. So these results generalize to any dual paired norms for x and the dual space of the gradients. Okay. And I'm not going to do I think I'm not going to do this. So there's some beautiful work of George Land, okay, that I've got here, but I don't think I have time for it, where he shows how to, this is a stochastic method. He smooths things stochastically, solves things with Frank-Wolfe. There's very, very beautiful work. I think this came out in June of 2013 that I wanted to show you if I had time. Here is brief references. I apologize if your work is not in here, but this is not intended to be comprehensive. Thank you very much.
Questions?
So my immediate answer is no. I don't know. Although in your opening remarks, you mentioned that there was some composite version of Frank-Wolfe that has just come out. So I don't know about that. And if its author is in the room, maybe, oh, that's your, oh, okay. Please. Okay, so see the recent work of Zaid Hachawi. Okay, yeah.
Other questions?
Yeah.
The equivalence between dual averaging and Frank-Wolfe, are the step sizes matching as well? So the good step size for one is a good step size for the other?
So with L2.
Between the equivalence between Frank-Wolfe and dual averaging.
Yes.
So for the two methods, you have specific step sizes that people use.
Yes.
Are they matching as well in your equivalence?
So yes, they are. That's right. Yes. Yeah. I mean, they sort of. Yes, they must. They must.
Yeah. Francis' question is the constants of L also match?
Yes, although there should be norm-free. There should be norm-free versions of all of this, but yes, in other words, but the basic answer is yes. Yeah. Yeah. Yeah.
So, follow up to Francis's earlier question. He commented on the linear convergence rate of Frank-Wolfe when your point is in the interior of the set. And your convergence rate, so I mean, it was dependent on the distance of the point from the boundary, or based on the symmetry of that point.
Right.
Now, do we know anything? He said that basically, if we know it's smooth, strongly convex, and it's in the interior, we could just do some gradient descent or something like that.
Right.
does that have, I mean, I'm not familiar, but I don't think that those algorithms have guarantees based on the symmetry or how far away the point is from the boundary or anything like that.
Actually, no, you're right. Huh? Yeah. All right. So let me just summarize the question as I understand it. Okay. So if we go back to this result here, okay. So the conditions, which you usually don't know, of course, but you never know when you're going to know things. All right. So that is, if you happen to know that X star is in the interior of your set, okay, and you happen to know that your function is strongly convex, all right, then you get linear convergence, and then you sort of think to yourself, especially if it's in the interior, why not use just a steepest descent type of method? Okay. Yeah, and you also get, of course, the linear convergence there. No, and you also get the U over L squared. And so, in a sense, I can't see any advantage of Frank-Wolfe over those methods.
But I think what I think he asked in his question was that in the gradient descent one, you won't have the distance to the boundary appearing.
No, but watch what I can do here. So in other words, that so suppose I know all of this. Okay. So suppose here is my point. Okay. I'll just toss my original set, and I'll just create some new set. I mean, I don't care what it looks like, so long as my point has perfect symmetry in that set. Okay. So then you get. So then basically, if we look at, say, this version of it here, this is 1, and then this is the standard steepest descent ratio.
Well, that's a symmetry of X star, not your current point. Right?
Yes.
You wouldn't know where that is.
No, you wouldn't.
But you could have
That's what I'm saying. Existentially, yeah. I mean, I feel this is a strange discussion, to tell you the truth. But let me summarize. I think the very good value of the line of questioning on this, which is right. In this case, okay, good. You get linear convergence, all right. But of course, you didn't need the machinery. If you wouldn't have needed the machinery of Frank-Wolfe, you could have just done steepest descent with the same or perhaps even better provable convergence rate.
But again, so steepest gradient is not it's not be adaptive, right? So this is, if it happened to be on the boundary, you'd still get the 1/k rate. If it happened in the interior, you'd get a linear convergence rate, and you didn't need to know about the strong convexity or
exactly.
the interiority beforehand.
That's right.
So isn't that an advantage?
Yes, it is. That's right. That's right. So in other words, yes. So right, this result says it's not the maximum here; it's the minimum. Okay, and so if you're lucky, without even knowing it, you're getting linear convergence. Right. Otherwise, you're just getting your vanilla Frank-Wolfe convergence result. I think we were probably out of time. Yeah. All right. So thank you very much.